Hi, chemistry students. This is your lesson on heat stoichiometry. You have likely been provided guided notes. Please pause the video as you need to look at the examples and consider how to do these problems. All right, so heat stoichiometry really works the same way as any other stoichiometry problem, except within the balanced equation, you will also have a term that represents the heat. So you'll start with a balanced equation, and you'll be given something, probably in grams like you usually are, but whatever you're given, you're going to need to convert that to moles. It's still based on a mole ratio. Now you're going to use a mole ratio, but this time, since heat is in the equation itself, it'll show the units kilojoules. That's the unit we use to measure heat. And you'll do a mole ratio, but this time you'll put on the top the heat term with kilojoules, and on the bottom, as usual, the given coefficient. Now, once you've done that, you're pretty much done because you're calculating heat in kilojoules. The best way to see this is by doing a couple of examples. So let's do a couple of examples, 2 examples, and also review what exothermic and endothermic are. All right, so this is the synthesis of ammonia from nitrogen and hydrogen gas. It has, as you can see on the product side, a term that says plus 92 kilojoules. And that's always assuming that we're talking about 1 mole, 3 moles, and 2 moles. That we're talking about mole quantities of these, not molecule quantities. This is 92 kilojoules per mole in this equation. Now, just to review, if this is on your product side, is this reaction endothermic or exothermic? If you said exothermic, you're correct. Heat is being released from this reaction. That's why it's on the product side. As you remember, when it's on the product side, you have a delta H that is negative, that energy is released, and more energy is stored in the reactants than in the products. So again, we are going to get a balanced equation. We are going to convert to moles if we need to. We're going to use a mole ratio with heat in kilojoules on the top and a given coefficient on the bottom, and then you're done. All right, so how many kilojoules of energy when 8 moles of ammonia is formed? So here's our balanced equation again. And as usual, we need to go up to the problem and find the given. That's 8 moles of ammonia. And this time we want to figure out how many kilojoules. So that's our wanted. Now, let's look at this. The first step is always converting to moles. But in this case, based on this problem, do we need to do this step? Do we need to convert to moles? And the answer to this is no, we've already got it in moles. So we don't have to change this to moles when it's already in moles. So our given is in moles. So it's really just the ratio step that we have to do. So we're going to do the mole ratio step. Oops, I'm showing it to you. And so like you got a little peek at that. But 8 moles of ammonia, okay, and we're trying to go to kilojoules. Now we're going to take the ratio from the balanced equation. So again, we're going to take this 92 and put it on top, and then we're going to find the given coefficient and put that on the bottom, because this is based on when we form 2 moles of ammonia, we get 92 kilojoules. So here is our ratio from the balanced equation, 92 kilojoules for every 2 moles of ammonia that are released. So we will do 8 times 92 divided by 2, and that will give us 368 kilojoules released. And again, 3 significant figures since we have 3 here and 3 here. Okay, let's try one more example. Yep. So, how much heat will be released when 6.44 grams of sulfur reacts with excess O2? Okay, so this is the formation of sulfur trioxide. And you can see we have a balanced equation. We see we have a delta H of negative 791.4 kilojoules. Again, if we have a negative delta H, is this exothermic or endothermic? And again, this one is exothermic because we have a negative kilojoules. Now we can rewrite this, remembering that this sign here just tells us the direction. It's not like it's different than positive 791.4 kilojoules. It's the same amount. It's just whether it's being released or absorbed and where it will go in the balanced equation. So I can rewrite this exothermic reaction like this. 2 sulfurs plus 3 oxygens give us 2 sulfur trioxides plus 791.4 kilojoules. And again, that takes into account the negative sign, showing that it's on the product side and being released. So let's see if we can do the problem now. All right, so we're going to rewrite and then identify the given and the wanted. Now remember, when we say with excess oxygen, we don't care, okay? We just want to do the one that's the number. So it is the limiting reactant, and we have the excess reactant, which we don't worry about. So the given is 6.44 grams of sulfur, and what we want is how much heat, and heat is measured in kilojoules. So that's what we're trying to get to. Now this time, do we need to convert to moles? Well, yes, because this is in grams. So here is how we will convert to moles. The first step here is the mole conversion. We have 6.44 grams of sulfur, and 1 mole of sulfur is 32.6 grams. So 6.44 divided by 32.06 gives us 0.201 moles of sulfur. Now we have to do the mole ratio step. So we're going to come up here and we're going to see for every 2 sulfurs we get 791.4 kilojoules. And so that's going to be our ratio, okay? So 6.44 divided by 32.06 gives us this many moles of sulfur, and then that times 791.4 kilojoules divided by 2 moles of sulfur are going to give us 79.485 kilojoules. Now, how many sig figs are we going to round to? Well, we've got 3 here, 4 here, 4 here, and these are exact numbers. So we're going to go with the least, which is 3. So we're going to round to 3 significant figures. So 79.5 kilojoules. And that is how you do heat stoichiometry problems. It really is much easier. You just, in the ratio step, you put the kilojoules on top, and on the bottom, as usual, you put the coefficient of the given from the balanced equation.